Welcome to the deep dive. When you're deep in the trenches of scientific discovery, especially when you're dealing with instruments and code, it often feels like you're experiencing something totally new.
Yeah, completely unprecedented.
But the veteran engineers, they'll always tell you that the fundamental struggles, they never really go away. They just reappear wearing different clothes.
It's that classic saying, right? History doesn't repeat itself, but it certainly rhymes.
It certainly rhymes. And that analogy just perfectly captures the massive technological cycle we're diving into today.
It really does.
Yeah.
We are tracing this huge arc that spans, nearly 3 decades. It's a revolution in how we design and build the incredibly complex software tools you need to capture, control, and analyze data from these really high-stakes physical experiments.
Absolutely. Our source for this deep dive is this fantastic, really detailed reflection from an engineer and academic, William L. Weaver. And he tracks his own journey, his personal and professional tech journey, from his early days back in 1988 all the way up to his lab today in 2025.
It's basically a roadmap, and it shows exactly how the definition of smart coding has just fundamentally flipped in his lifetime.
So our mission today is to trace that evolution, and I think this is the critical part, to understand what Weaver calls the anti-gravity renaissance.
Right, and it's a story that's really defined by this constant tension between two camps. On one side, you have the keyboard warriors, the engineers who define their merit by mastering syntax, by handwriting every single semicolon.
The purists.
The purists, exactly. And on the other side, you have the systems thinkers, the scientists who are just relentlessly focused on the architecture of the system, the integrity of the physics, and the data it produces.
And we have such a phenomenal arc to cover. It is filled with technical agony and these profound moments of total release. We're going to look at the sheer, unadulterated pain of dealing with over 21,000 lines of hand-coded stack management in a language called Forth.
Oh, well, the pain is real.
And then the salvation that arrived with a tool called LabWindows CVI in the early 90s. Then the big academic shift to visual programming with LabVIEW.
Right.
And then finally this revolutionary leap we're seeing today into generative AI frameworks like antigravity.
It's a full circle narrative.
Yeah.
It really is. The journey starts with the scientist being, fundamentally subservient to the language, right?
Completely at its mercy.
And it ends today with the tools finally becoming subservient to the scientist's intent, the way it always should have been.
So let's unpack this. We have to start right at the beginning, at the absolute foundation of struggle, because before all the revelations, before the automation, there was just this manual grind of the late 80s and early 90s.
You have to understand the pain to appreciate the relief.
Exactly. This is the context we need to really appreciate the technological leaps that came after.
That's right. And Weaver, he starts his reflection well before he was building complex laser diagnostics. He was learning computing, on the ground floor. He mentioned starting with a Timex Sinclair 1000.
Wow, that's a throwback.
It is. A machine that required incredible patience and gave you almost zero resources. But, for that generation of curious engineers, that was the entry point.
And his formal training wasn't in Python or Java or anything we'd recognize today. We're talking about the legacy workhorses.
Oh, yeah. COBOL and Fortran.
Yeah.
Learned in high school. These are languages that are just steeped in this very procedural discipline. They were designed for structure, for mainframes.
That foundation, that procedural foundation, feels really key because by 1988, he was already applying that knowledge in a really practical way. He wrote a custom inventory system for his father's print shop.
Using Borland Turbo Basic, yeah. And this wasn't just, some academic exercise. This was solving a real-world business problem.
Right.
And it kind of establishes his core motivation from the very beginning. It's about system optimization. It's about getting results. It's not just about coding for the sake of coding.
But the real technical agony, the crucible moment that really set the stage for everything that followed, that came during his graduate work at Ohio State. He was building these incredibly sophisticated scientific instruments, but the tool he was forced to use was something called the Asyst dialect of Forth.
And Forth it's arguably one of the most intellectually demanding languages of that whole era, especially when you compare it to what else was around. It's based on postfix notation, and it relies entirely on a data stack.
Okay, so let's break that down. Postfix notation, for anyone listening, you might know it as reverse Polish notation. So instead of writing 3 + 4 = 7.
Right, you'd write 3, 4 + 7. You put the operands first and then the operator.
So the computer isn't handling all the temporary storage and variables behind the scenes.
Yeah.
You, the programmer, you are constantly acting as the stack manager.
That's it. You are explicitly telling the computer every single step. Push this value onto the stack. Now push the next value onto the stack. Now perform the operation. Now clear the stack. Now take the result off and store it.
Manually. For everything.
Precisely. And this is so vital to understand the psychological cost of this. Every single line of logic requires you to explicitly manage that stack. If you forget a push, or if you accidentally leave some data on the stack that then messes with the next operation.
The whole program just fails.
It just fails, and often without a clear error message. So this just dramatically increases the time you spend debugging these really simple memory and structural issues instead of focusing on the actual physics of your experiment.
And the sheer volume of this manual labor is just staggering. His dissertation code had accumulated over 21,000 lines of hand-coded stack operations.
Over 3 years.
Over 3 grueling years. I mean, can you even imagine? 21,000 lines. That is 3 years devoted not just to the actual science of his thesis, but to literally micromanaging the computer's memory stack.
Think about that cognitive load. I mean,
Yeah.
in modern C++ or Java or Python, the compiler and the interpreter, they handle all of that low-level memory management for you automatically.
You don't even think about it.
You don't. Weaver was, in effect, writing a machine-level driver just to run his high-level experiment. That 21,000 lines, it represents this mountain of friction standing between the scientist and actually getting their data.
It's the definition of a tool dictating the pace and the effort required rather than enabling it.
Absolutely. That number just really underscores the exhaustion, the delay it must have caused. It highlights a period where the barrier to doing a high-stakes science was literally the complexity and the just, unforgiving nature of the programming language syntax.
And that level of friction, that pain, it makes the pivot point in 1993 completely understandable. When he moved to Wright-Patterson Air Force Base, he wasn't looking for a new hobby.
No, he needed speed. He needed efficiency. He needed a platform that could actually handle the complexity of ultra-fast laser diagnostics in a modern Windows environment.
The foundational struggle basically set the stage for a desperate search for a better way.
It did, and that search led directly to Section 2. The revelation. The moment the tools finally started working for the scientists, not against them.
And this was all courtesy of National Instruments and a product called LabWindows CDI. This must have felt like going from, I don't know, using a chisel to a power saw.
It was tectonic.
Yeah.
I mean, that's the only word for it. CVI stands for C for virtual instrumentation. It was this brilliant bridge product. For Weaver, coming from the highly procedural trauma of Forth, CVI must have felt like a monumental leap forward.
Even though it was still based on the C language.
Even though it's still fundamentally C. That's the key.
Okay, so let's unpack CVI specifically. The revelation wasn't that it invented some brand new language. It was that it offered this intelligent scaffolding on top of a professional standard. What did it provide that just immediately solved that old Forth problem?
It basically democratized low-level control while keeping all the power of ANSIC. It wrapped all these C libraries in a really sophisticated integrated development environment, an IDE, and the features he mentions, true autocomplete integrated function panels and automatic code generation for user interface callbacks, those were revolutionary in that context.
Let's focus on those UI callbacks for a second. Because in the 90s, if you wanted a button on your screen to, say, start a data acquisition process,
Oh, good luck.
you had to write pages of highly detailed platform-specific code just to manage the Windows handle, capture the mouse click, and then link it to your underlying C function. It was a nightmare.
It was a total nightmare. And CVI handled all of that grunt work. You could visually place a button on the screen, and the IDE would automatically generate the boilerplate C code that managed the window handle, the mouse input, the connection to the operating system.
So it freed the engineer from spending days, maybe weeks, writing platform-specific syntax just to get a basic screen element working.
Exactly. The mental energy could immediately shift to the important stuff, the data processing logic, the instrument communication, the actual physics of the experiment.
But this advancement, it immediately sparked controversy, which is the recurring theme here, isn't it? The resistance from the self-described real programmers, the ANSIC purists.
Oh yes, the keyboard warriors. They saw CVI as a crutch. They truly believed that if you weren't manually managing every single pointer and explicitly writing the code to handle a button click in raw C, you weren't really mastering the craft.
Your whole identity was tied up in their ability to conquer that low-level syntax.
It was, and it's fascinating how that same reaction just echoes throughout technological history, right? Machine code experts resisting C, C experts resisting Java, and now...
And now traditional coders resisting AI.
Exactly. But Weaver provides the definitive data point that just completely refutes the crutch critique. Over 7 years, he generated more than 100,000 lines of production-ready code using CVI.
100,000 lines.
That volume is so critical, it proves the tool was an accelerant, not a substitute for skill. You don't produce 100,000 lines of complex, reliable working code using a crutch.
No, you produce it using a powerful leverage tool that removes all that arbitrary friction. He wasn't building, simple little demo programs. He was managing industrial-grade instrumentation.
Yeah, let's delve deeper into the complexity of the work itself, because this is where the power of CVI really let that high-level intelligence shine. He was managing low-level instrument communication via these old legacy standards, like GPI.
GPI, so that's the General Purpose Interface Bus, the old IET 488 standard.
Yeah.
That was the standard way to connect lab instruments, right, like oscilloscopes and multimeters, to a computer.
It was, and crucially, communicating over GPI manually meant you were managing hardware addresses, polling cycles, really strict low-level timing protocols. If you did this in raw C, it was just tedious and so error-prone.
So what did CVI do?
CVI provided pre-built function panels and drivers that just abstracted that entire painful layer away. It turned what would have been a week of low-level driver coding into just a few function calls.
And beyond just simple communication, he was using sophisticated tools like the NI-IMAQ library for complex matrix manipulations. That was for his optical diagnostics. What does that specifically involve?
So optical diagnostics, especially in the kind of laser environment he was in, rely heavily on image processing. The IMAQ library specialized in really rapid manipulation of large matrices, which is just the raw pixel data from the cameras.
Okay.
When you're trying to track phenomena like ultrafast laser pulses or gas flows, you need to perform things like Fourier transforms, convolutions, or image subtraction on massive data sets in near real time. This requires extremely optimized fast code.
So CVI gave him the framework and the optimized libraries to handle all that computational heavy lifting.
Right. It let him focus on designing the mathematical filter for his experiment rather than wrestling with the low-level memory allocation of the matrix itself.
You also mentioned these proprietary tweening algorithms he developed.
Yeah.
To track test article deformation during wind tunnel buffeting. This sounds like a perfect example of system intelligence overriding that syntax struggle.
It truly is. Tweening here is a highly specific, proprietary form of interpolation and image correlation. So imagine a test article, like a small wing inside a high-speed wind tunnel. When the air hits it, it doesn't just sit still. It vibrates, it bends, it deforms really rapidly, it buffets. To understand its structural integrity and the aerodynamic forces, you have to track that deformation in 3 dimensions at extremely high speed.
So he's not just taking a single snapshot. He's taking hundreds of frames per second and trying to mathematically figure out the exact displacement vector of every critical point on that object, frame to frame.
Precisely. And this requires custom high-speed algorithms that analyze these subtle pixel shifts between frames, correlate those shifts to known physical points, and then interpolate the motion, that's the tweening, between the measured data points to create a smooth, accurate timeline of the deformation.
And the fact that CVI handled the GPIB, the IMAQ, the GUI boilerplate, that allowed him to focus months of effort on perfecting this proprietary mathematical model.
That is the leverage a smart tool provides.
Yeah.
Then it brings us to the ultimate anecdote that just drives home the distinction between a keyboard warrior and a systems thinker, the 6-camera system.
This is a brilliant example of solving a physics problem with architectural ingenuity, all enabled by the software.
This is really the apex of CVI's utility in Weaver's early career. The goal was this incredibly sophisticated 3D entrained particle velocity measurement. It used 3 pairs, so 6 cameras total, all running simultaneously.
And they were using some pretty specialized techniques, right? Doppler shifts and gas-filled optical filters to measure the movement of air and particles inside the wind tunnel flow.
Yeah, very cutting-edge stuff for the time. But they hit a massive technical wall. And it was inherent to 1990s PC architecture.
The limitation wasn't the science.
No, it was the I/O bottleneck, the input-output bandwidth of the PC bus. In that era, the standard PCI bus simply could not handle the instantaneous data throughput for more than 2 high-speed digital cameras feeding into a single machine.
Especially if they're all triggered at the exact same time.
Exactly. The bus would just saturate, you start dropping data packets, and the entire experiment would fail.
So a traditional programmer, a keyboard warrior, might have just accepted the limitation. Well, I guess we can only use 2 cameras.
Right. The hardware says no. But the systems thinker, who's been freed by CVI from all the syntax concerns, says, no, we just need a distributed solution.
And that architectural solution was to distribute the data capture.
Exactly. They use CVI applications running on multiple distributed PCs, each one handling 2 cameras, and they triggered all 6 cameras simultaneously across the network. The challenge then became getting that massive high-speed data set back to a central hub for processing without losing synchronization or any data packets.
And here's where the high-level custom code comes in. Weaver wrote a proprietary custom TCP/IP protocol to funnel all that image data from the distributed computers back to the central hub.
And this is so critical. Why custom? Because standard protocols like FTP or even basic HTTP transfers, they introduce latency and a lot of overhead.
Right, they're built for reliability over raw speed.
Exactly. For this real-time, high-volume image data, they needed a specialized protocol that was tailored precisely for fast, lossless transmission of these large, continuous data blocks. It bypassed all the unnecessary networking layers.
It's just a powerful lesson. The tool CVI, it handled the boilerplate and the drivers, which allowed the engineer to solve a distributed computing problem that was caused by a fundamental physics and hardware limitation.
That's the first successful loop in our history, Ryan. A smart IDE empowers the engineer to focus on the system, not the syntax. They were defining system architecture, not wrestling with Windows API calls.
And that level of efficiency made Weaver an incredibly productive researcher for years.
It did. That alignment between the researcher's needs and the tool's capability, that's really the definition of a golden era.
But as we move into Section 3, we see that alignment, especially when it's built on proprietary systems, can disintegrate really quickly due to forces completely outside the scientist's control.
Yeah, the shift began around 1999. Weaver transitioned back into academia at LaSalle University, and he pivoted from CVI, which was text-based C, to the visually based LabVIEW, also from National Instruments.
And for his new role, running this integrated science, business, and technology program, LabVIEW seems like it would have been the perfect fit. Why did that visual flowchart-based environment work so incredibly well for teaching systems thinking?
Because LabVIEW is intrinsically a data flow language. You don't write sequential lines of code. You draw these functional blocks and you connect them with wires that represent the flow of data.
So it forces you to think visually?
It forces students to think about the inputs, the processing blocks, and the outputs, the architecture, before they can even run the program. It perfectly mirrored the systems thinking curriculum he was teaching.
So they could map a physical process or an algorithm directly onto the graphical environment.
Exactly. And the result was this massive acceleration for students. He noted he could take undergraduates with, zero computer science background and have them building machine learning data analysis systems in a matter of weeks.
Wow.
It was an amazing ability to abstract away the syntax barriers. It allowed for rapid prototyping and immediate focus on algorithms and system architecture. It was, as he calls it, a golden era for university research and education.
But then came what Weaver terms the drift. The technological landscape shifted, and the proprietary tools began to strategically move away from their core academic users.
The catalyst for that change seems to be the corporate shift at National Instruments. The retirement of Dr. James Truchard in 2017, one of the company's founders, that marked a real philosophical change.
And that was followed by the eventual acquisition of NI by Emerson in 2023.
Right. And corporate mergers, they invariably mean reassessment, and often a shift toward high-margin industrial customers over, academic or hobbyist users.
So how did that strategic shift manifest in immediate, painful, practical terms for Weaver and his lab?
It was a brutal triple whammy that just cut the academic lifelines. First, the academic volume licenses changed. They became bureaucratic, restrictive, and more expensive, which immediately impacts accessibility.
Okay.
Second, crucial hardware support vanished. The support for flexible, inexpensive third-party hardware like Arduino, which is essential for low-cost, decentralized academic projects, that was deprecated.
And the third hit was the loss of capability. Essential modern tools like web development modules,
which are critical for building distributed browser-based interfaces to remotely control lab instruments.
They just vanish.
They vanished from the standard packages, or they became these prohibitively expensive add-ons. So if you can't get your license, you can't use cheap hardware, and you can't build a modern remote control interface, the tool has stopped enabling your mission.
It's become a blocker.
It's become a blocker. And this leads to those two agonizing years from 2021 to 2023, where Weaver was fighting what he calls a war on two fronts.
Let's talk about that administrative pain, because this is where the proprietary system really showed its weakness.
Front one was the internal friction, the university bureaucracy. Just imagine trying to renew a proprietary license for a complex software suite. It involves purchasing departments, IT administration, compliance checks,
Dedicated licensing servers that need constant patching.
and compatibility issues with Windows environments that are locked down for security. It's a nightmare.
It's a delay loop. You submit the paperwork, purchasing takes 3 months to approve it, then IT discovers the new version doesn't integrate with the existing network security configuration.
Right.
And suddenly the software that should take 30 minutes to install takes 6 months of interdepartmental negotiation.
That administrative effort becomes this massive, non-productive tax on your research time. Weaver was spending more time fighting the Windows licensing server and IT gatekeepers than he was analyzing his data.
That is the new form of friction. It's replacing the old fourth stack management problem.
It is. And front two was the external reality. The tool itself was strategically moving away from him. The new NI AI support system, which had the codename Nigel, which Weaver had pinned his hopes on for future features.
It was immediately unreliable.
He notes that Nigel was offline more often than he was online. And this just showcases the extreme vulnerability you have when you rely on a proprietary ecosystem for your research. If the vendor shifts focus or if their new features are buggy.
Your entire research agenda just grinds to a halt.
And the result was agonizing delays. He states it very clearly. The SAIL team was grounded. After decades of technological innovation and system building, they were stopped. Not by a failure of physics, not by a lack of intellect, but by broken licensing servers and administrative bureaucracy.
It's the ultimate betrayal of the systems thinker. His ingenuity was rendered completely useless by paperwork.
That administrative agony makes the eventual decision to abandon the entire proprietary struggle and the entire Windows and NI ecosystem completely logical. It was necessary for survival.
Which brings us to Section 4, the Renaissance. The moment the pendulum swings back, not to another existing proprietary solution, but to the next evolution of intelligent, open tools embracing the anti-gravity framework.
Weaver's frustration, it reached a boiling point, and it led to this necessary statement. I've abandoned the struggle with proprietary licensing servers and Windows patches. This is the move to an open, flexible ecosystem. It was a radical change, but it was driven purely by the need to regain control over his own laboratory and his research timeline.
Let's detail the new development stack he embraced in 2025, because it really is a blueprint for modern, resilient, high-level scientific system design, completely divorced from those proprietary dependencies and licensing fees.
It's a heterogeneous, layered stack, and it's designed for maximum resilience. At the core, he's running the Google Antigravity framework on Debian 13.
So Debian, one of the most stable and open source Linux distributions you can get. That immediately solves the Windows administrative friction right there.
Gone. The hardware control is managed by C++ firmware running on Arduino controllers. These are ubiquitous, they're inexpensive, and they're fully supported by the open source community.
And the high-level system logic, the data processing, the storage, the API management, that's all handled by Python with Flask for the backend.
Right. Python is the modern standard for scientific computing, and Flask is a lightweight, super effective web framework. The user interface, the modern replacement for those old CVI graphical panels, is built with Node.js for the front end.
And crucially, all of this is housed on GitLab,
which ensures seamless version control and collaboration without needing external proprietary licenses to coordinate team members.
That stack is designed for resilience. I mean, if Google shifts its focus on anti-gravity, the underlying components, Debian, Python, Flask, Node.js, they all remain open and functional. It mitigates that risk of the drift that he's suffered through with NI.
Exactly. It transfers power back to the user. And within this powerful open environment, the generative AI component, specifically Gemini 3.0 Pro in the anti-gravity framework, that becomes the new CVI.
You called it the ultimate autocomplete, and that's the critical comparison he draws right back to that 1993 revelation. He says working with this generative model feels viscerally like the early days of CVI, but it's solving modern web-based complexity instead of 90s GUI complexity.
It's the same feeling, different problem. In 1993, CVI generated the tedious boilerplate for graphical user interface elements. Today, when Weaver is building his new sensor network, he asks the generative AI model to handle the modern boilerplate. He asks it to scaffold a Flask route.
Okay, so for our listeners, a Flask route is basically the instruction manual for how the server handles specific web requests, how data gets sent from the sensor through the server and out to the browser interface.
Yeah.
Manually setting up those routes with proper error handling and data serialization, it's extremely verbose.
It is the new administrative friction. The AI removes that friction. He also asks the model to optimize a C++ interrupt service routine, a highly technical piece of firmware code on the Arduino that needs to be perfectly efficient to capture high-speed sensor data without lag.
So the AI provides the optimized structure, and that allows Weaver to just verify the physics and the timing rather than wrestling with the C++ syntax and memory management.
Exactly. The generative AI is not solving the fundamental proprietary physics problems. It's removing the modern-day equivalent of the 1993 GUI callback problem or the 1988 Forth stack management problem. It handles the structural syntax and the architectural plumbing of a distributed web system.
That is the profound truth of the full circle thesis. Weaver argues that this isn't cheating, which is the current pejorative of choice or, vibe coding. Generative AI is simply the ultimate form of abstraction and automation for modern interconnected systems.
But wait, let me push back on this point a little. Isn't relying on generative AI, especially one from Google, just exchanging one proprietary master, National Instruments, for another in Google Antigravity? I mean, how resilient is that stack truly against another corporate drift?
That's a crucial, high-level question, and I think the answer really lies in the architectural choice he made. While antigravity may be a proprietary framework, Weaver has deliberately embedded it within an entirely open-source architecture. Debian, Python, Flask, Node.js.
Okay.
So if Google decided to deprecate antigravity tomorrow, the underlying structure of his entire system remains sound. He would lose the rapid scaffolding capabilities of Gemini 3.0 Pro for sure, but the C++, BP, Python, and WebLogic would all continue to function and could be supported by standard tools.
So it's not the same dependency lock-in that he experienced with the all-in-one Windows solution.
Not at all. The key insight is that he has decoupled the AI accelerator from the underlying system integrity. The system can survive the loss of the accelerator. That was not the case when his code was inextricably tied to NI drivers and Windows handles.
That decoupling is the architectural genius of the anti-gravity renaissance. Just as CVI allowed him to focus on the physics of the laser rather than the syntax of the Windows handle, anti-gravity lets him focus on the architecture of the sensor network and the timing of the C+ interrupts, rather than the boilerplate of the API and the licensed server administration.
The tools are radically different. Turbo Basic gave way to Forth, which yielded to CVI, then LabVIEW, and now Generative AI. But the goal remains constant.
The independent variable, the thing that stays constant and matters most, is the researcher's systems intelligence and their knowledge of the science. The dependent variables, the tools, have simply evolved to match the needs of the system designer, and they're always aiming to remove the next highest barrier to execution.
And the success is tangible. After years of administrative delays that grounded the team, the first system in the new lab, built entirely on this open-source anti-gravity stack, is operational.
And Weaver is focusing entirely on the scientific results, ignoring the critics who are still using vibe coding as a pejorative. It's a powerful, really satisfying conclusion to his professional journey.
The tools have finally caught up again to truly serve the researcher's intent. They've removed the arbitrary friction that once defined his graduate work and later defined his administrative agony.
This entire journey provides just a phenomenal synthesis. It traces the constant quest in instrumentation science to remove these arbitrary barriers between the scientist and the hard, necessary data.
The historical rhyme is crystal clear. In the early days, the barrier was the raw complexity of the machine and the language, those 21,000 lines of Forth stack management.
And then proprietary smart IDEs like CVI and the visual environment of LabVIEW, they lowered that barrier. They shifted the focus to graphical data flow and system architecture.
But then the proprietary model created massive new administrative barriers, the friction of licensing fights, the deprecation of useful hardware, and these corporate strategic shifts that just stopped the research cold.
And now, open source architectures combined with generative AI have bypassed those administrative barriers entirely. They offer the highest level of sophisticated scaffolding yet. They eliminate the syntax and boilerplate that once caused friction, whether that friction was 1988 memory management or 2024 web API management.
The philosophical takeaway for anyone listening, whether you're an engineer, a scientist, or just someone trying to leverage new tech, is that mastery isn't found in memorizing syntax. It doesn't matter if that syntax is Forth stat commands or the latest Flask library calls.
It is about understanding the system architecture, the physical principles, and how to effectively control the experiment and interpret the data. The keyboard warriors are always debating the tools. The scientists are debating the universe.
And modern tools, no matter what they're called, are simply accelerating that research process. They accelerate the path from hypothesis to execution, which is the only thing that truly matters in scientific discovery.
And that acceleration is the defining feature of the anti-gravity renaissance. It is giving the system designer back their most precious commodity, time. Time that used to be spent arguing with IT or micromanaging stack operations is now spent designing better algorithms and running more complex experiments.
Which leads us to our final provocative thought for you to chew on as you go about your week. We've established that the previous generation called CVI a crutch, and the current generation is calling generative AI vibe coding or cheating.
The pattern is established. Any new tool that removes mandatory low-level effort, the tedious labor that was once required to prove your competence, will be labeled cheating by those whose competence was defined by that very tedious labor.
So consider this. If generative AI successfully makes all boilerplate API writing, all Flask root scaffolding, and even sophisticated C++ optimization completely obsolete, what new fundamental skill, which is currently profound and complex, may be related to global sensor architecture, data trust, or quantum error correction, what will be the thing that the next generation of coders calls cheating?
And what new profound discoveries will those highly accelerated skills unlock in the coming decades? The only constant is change. And the only certainty in this technological rhyme is that the best tools are always the ones that empower the user by getting completely out of the way.
Thank you for joining us for the Deep Dive. We'll see you next time.